Hi, everybody. It's Professor Mitchell. We have reached the last section of Chapter 3 on exponential and logarithmic functions. Today, we're going to be talking about exponential growth and decay. So the objectives of this section, actually, we're only going to cover a few of these. Really, we're just going to model exponential growth and decay. So the mathematical model for exponential growth or decay is given by f of t equals a sub 0 times e to the kt, or a equals a sub 0 times e to the kt. If k is greater than 0, the function models the amount or size of a growing entity. A sub 0 is the original amount or size of the growing entity at time t equals 0. A is the amount at time t, and k is a constant representing the growth rate. If k is less than 0, then the function models the amount or size of a decaying entity. But all the other stuff you see here, I think, is the same as on the previous slide. A sub 0 is the original amount, a is the amount at time t, and k is a constant representing the decay rate. So here's an example. In 2000, the population of Africa was 807 million, and by 2011, it had grown to 1,052 million. Use the exponential growth model A equals a sub 0 e to the kt, in which t is the number of years after 2000, to find the exponential growth function that models the data. So like I did in the last section, I'm going to work these problems out on the tablet. They are a little involved, and so I think you might get a little more out of that than if I just try to bring it up on the screen here. So what I have done on my tablet is I've written down the growth model, A equals a sub 0 e to the kt, and then the given information translates like this. So a sub 0, which is the original amount, is 807. Okay, so we're going to measure the population in millions. And they tell me that a equals 1,052 when t equals 11. So in this problem, we're just trying to complete the model, which means just finding the value of k. So you'll find that a substantial part of doing these problems is finding the value of k. That is usually not given. All right, so I'm going to put in the information that I have. So first I'm going to say a equals 807 times e to the kt. And now I know that when t equals 11, sorry, I'm just trying to do a little color coding here. When t equals 11, a equals 1,052. So now we can solve this equation for k using the methods that we talked about in the last section. So we have 1,052 equals 807 times e to the 11k. So the first thing I'm going to do is divide both sides by 807. At some point, I'm going to need to have my calculator handy, so let me get that fired up. There we go. Okay. All right. So now we have 1,052 over 807. If you wanted to, you could turn that into a decimal. Just be very, very careful, especially in these problems involving exponential functions. Be very careful about rounding. All right, round as little as possible. I would say keep a minimum of 4 decimal places in every number, especially numbers that appear inside exponents. So I'm not going to do any rounding until the end of the problem. 1,052 over 807 equals e to the 11k. All right, so what we talked about in the last section is you can, let's see, how did we say this in the last section? Maybe the simplest way to think of it is just take natural log of both sides. I think that's actually exactly how we did it. Okay, so we have natural log 1052 over 807 equals natural log e to the 11k. And then by the inverse property of e to the x and natural log x, natural log of e to the 11k is just 11k, right? We talked about that in the last section. So we have natural log 1052 over 807 equals 11k, which means k is natural log 1052 over 807 divided by 11, which is approximately 0.0241. Okay. All right, so that means I'm going to squeeze this up top because I've already got something written on the next slide. That means that our exponential growth model for the population of Africa is A equals 807 times e to the power 0.0241 t. Okay. All right, so let's switch back to the presentation. I have a follow-up question about this problem. Okay, here's what we did. Looks exactly like what we did. Oh, they rounded theirs to 3 decimal places. Okay. All right, so follow-up question. By which year will Africa's population reach 2,000 million? In other words, 2 billion. Okay, so going back to the tablet, let me go to the next page here. By which year will Africa's population reach 200 million? So using the model that we just found, which is A equals 807 e to the power, I'm going to stick with my 0.0241. Probably won't make any difference, but. All right, they want to know what is t when a is 2,000. So this is kind of similar to what we just did, except this time we're solving for t instead of solving for k. So we have 2,000 equals 807 e to the power 0.0241 t. So the first thing I'm going to do is divide by 807. Goodbye, goodbye. That's going to give me 2,000 divided by 807 equals e to the power 0.0241 t. So now, just like in the last problem, I am going to take natural log of both sides. Natural log 2,000 divided by 807 equals natural log e to the power 0.0241 t. And again, by inverse property of e to the x and natural log x. Natural log of e to the power 0.0241 t is just 0.0241 t. All right, so now I'm going to divide both sides by 0.0241. Remember, I'm trying to find what is t. And what I get is t equals natural log 2,000 divided by 807 divided by 0.0241, and that is approximately 37.6588. Okay, and the question was by which year? So of course years are always expressed in whole numbers. So we'll round that to 38. Now remember, T represents the number of years after 2000. So this means 38 years after 2000, the population will reach 200 million. That means by the year 2038. Okay. It's not too hard, especially once you get used to it. All right. So this all looks familiar. All right, moving on to the next example. So this is a half-life problem. Classic application of exponential decay. The half-life strontium-90 is 28 years, which means that after 28 years, a given amount of the substance will have decayed to half the original amount. Find the exponential decay model for strontium-90. So this is kind of similar to the first problem that we did with the population of Africa. We're just looking for a model, which really means that we're looking for the value of K. All right, so I've got this written down. So up top there, you see your exponential decay model. We're expecting the value of K to be negative this time. Remember, in exponential decay, that value is negative. And the given information translates like this. When T equals 28, A, which is the amount after T years, is 1/2 the original amount. Okay. So here's how I'm going to put that into the equation. I'm going to replace A with 1/2 A0. And I'm going to, of course, replace T with 28. Okay, here we go. All right. So this is an equation that I can solve for K. The first thing I'm going to do, let's pull up a different color here. First thing I'm going to do is divide both sides by A sub 0. And notice what happens. Not only does it disappear from this side, it also disappears from that side, which reveals a really important fact about, well, I think about exponential decay in general, which is that when they say the original amount present decays to half after 28 years, that doesn't depend on exactly how much is present to begin with. All right, the specific amount present to begin with doesn't matter. It will always be half of whatever that original amount was after 28 years. So we have 1/2 equals e to the 28k. All right, and now I'm going to do the same thing I did in the previous two problems. I'm going to take natural log of both sides. So we have natural log 1/2 equals natural log e to the 28k. And once again, by the inverse property of e to the x and natural log x, natural log of e. Okay, so now we'll divide both sides by 28. And we get that k is natural log 1/2 divided by 28, which is approximately negative, like we expected, 0.0248. I'm going to call that. All right, so our exponential decay model is A equals A0 e to the negative 0.0248 t. All right, and again, they have a follow-up question. All right, so there's that. That looks familiar. Okay, so we found the exponential decay model. If there are originally 60 grams, how long will it take for strontium-90 to decay to a level of 10 grams? All right, so one last time, we'll go back to the tablet. And here's how that translates. So remember, our model was A equals A0 e to the negative 0.0248 t. Okay, so the question is, what is t if 10 is equal to 60 times e to the negative 0.0248 t? All right, so we'll start by dividing both sides by 60. Okay, that gives us 10 over 60, which I can't stand to leave like that. I'm going to write it as 1/6. Equals e to the negative 0.0248 t. All right, so now we'll take natural log of both sides. We have natural log 1/6 equals natural log e to the negative 0.0248 t. And once again, that inverse property of e to the x and natural log x is going to say that the right-hand side of that equation simplifies to negative 0.0248 t. All right, so now I'm going to divide both sides by negative 0.0248 by negative 0.0248. And I think I can squeeze this in over here. Therefore, t is natural log 1/6 divided by negative 0.0248. And that is approximately, now hold that thought. We can get an idea of what a reasonable answer should be for this. So remember, every 28 years, it decays to half its original amount. So if we start with 60, after 28 years, there would be 30. After another 28 years, there would be 15. Okay, so the answer should be more than 56 years, but it wouldn't be another 28 years because after another 28 years, it would decay to 7.5. So the answer is somewhere between 56 and what is that, 84? 28 times 3. So let's see, what is it? Natural log 1/6 divided by negative 0.0248. Yes, 72.248. So we'll call that 72.2. It takes just a little over 72 years for a sample of 60 grams of strontium-90 to decay down to 10 grams. I wonder how they rounded their answer. They rounded it to 72. Okay, that's reasonable. And that's actually all I have for this section. We're not going to cover some of the other things that you saw listed in the objectives. So take care, and we'll see you next time.